Kaydı başlattım. Evet. Evet arkadaşlar, bu haftanın konusu vizelerden sonraki ilk konumuz çarpma, multiplication, I multiplication, division, bölme, I division. Bu I'lar signed value'larla işlem yapabilmek için olan instruction'lar. I multiplication'da signed multiplication'ın anlamları. 4 tane sorumuz var. 2 tanesi çarpma, 2 tanesi bölme. Bunları işleyeceğiz. Evet. Let me switch into English. Okay, my friends. Today's instructions, the new instructions are multiplication and divisions. When we see a new instruction, remember we open the help and look for the instruction set and open the new instruction manual. Multiplication only has one parameter, which can be register or memory, and it only do multiplication, but this is unsigned multiplication. Algorithm is simple, but it depends on the parameter size. For example, if the parameter is byte, the algorithm is this. If the parameter is word, the algorithm is this. Okay, this is understandable. The parameter is here, byte times AL stored in AX. This is understandable. But this part may be complex to you. Remember, in 32-bit integers, we split the 32-bit integers into two parts, 16-bit parts. We are doing the same thing in here. When you multiply 16-bit operand, which is word operand, with AX, the result will be stored in DX AX couple. Okay, so the upper part of the result will be in DX, the lower part of the result will be in AX. Let me copy this example. Okay, for example, AL has 200, BL has 4. Multiplication. We keep using AX or AL in our multiplications. It didn't change. If it is byte, it multiplies it with AL. If it is words, it multiplies with AX. Okay? So this is byte. The calculation is AL times, let me put X, not asterisk. AL times BL is stored into AX. This is the algorithm this third line is doing. Okay, the result is 800. Let's see. Okay, AL has 200, which is C8. We go in here. 200. BL is 4. Multiplication is done. The result is in AX, which is 320. 320H, which is 800. Unsigned. This is unsigned multiplication. Okay. You can change this into memory. For example, let's put this into 1000H address and multiply AL with 1000H address. This time sorry, not ALBL. This will be 1000 H address. Okay, 204. Let me go over and look at the 1000 H address. 4 is here. The result is in AX. Let's put result in, for example, 1005 H address. The result in AX. Okay, multiplication is done. The result is stored in 1005. The result is AX, that's why it is 2006 and 2005. These two byte value is our result, which is 330H, which is in decimal 800. Okay, you can't multiply other than A register. It is instructed this way. So for example, when you want to multiply CX with DX, you have to use a medium, which is AX. You have to use a medium, which is AX, or CL and BL. You have to use a medium. You have to, for example, put one of them in AL and multiply DL. This is the multiplication of CL with DL, and the result will be in AX. Okay. So the next instruction, I multiplication. I multiplication exactly do the same thing, but it look for the signed values. It, how can I say? I can't say that. Sorry. You can't multiply signed values with mul instruction, because this did not look for the signed part. That's why the multiplication of signed numbers with mul instruction will result into wrong calculation. Not always, but generally. For example, let's change this number into negative value and see the result. The result is minus 800. And minus 800 is, let's go and not scientific, programmatic, minus 800, which is FCE0. The result will be in AX, and the result is FCE0. Okay, we already emulated. Minus 4 is in 1000 and 1000 address, which is FC. Okay, the result in AX. For example, the result should be FCE0, but the result looks like C4E0. So this is wrong. When you open this and look at the numbers, none of these are the correct value. So we use the wrong multiplication. But when I change this multiplication into I multiplication and emulate, okay, the same numbers, and the result is in AX. And we open this. Why it didn't calculate correctly? I multiplication. Let me reload this. 200 minus 4 I multiplication with -4. The result is E4, not just E4. There's something wrong with this. 200 -4. Let me use medium. I multiplication. Let me check the help. Where is the I multiplication? Yes, it can also take memory. I multiplication result is 8. Signed multiply. Yep. L. Yep. Erase these ones. And we put AX into here. 200 -4. This is -4. Signed value -4. Yep. 200. This is 200. Oh. That's why. This is not 200. 200 is, let me open it here. 200 is C8. Okay. When you put C8 in the AL, signed value of C8 is -56. For my interesting example, -56 times -4. 56 times 4, which is E4. The result, remember, is E4, E0, because it multiplies -56 with -4. Why it takes 200 and convert it into -56? Because signed value of AL can be fit into -28 to 128. 127 and 128. If the value is not between this range, for example, in this case 200 is above this case, so it becomes minus. Yeah. When we put 200 in AL, signed value of 200 is actually -56. So you can't multiply 200 with -4. In order to multiply 200 with -4, I'm going to use AX. Let's use it this way. But it should be BX2. Okay. This time it is 200. Why? Because we look for the AX, signed value of AX. These are same now. Okay, -4. -4 is FFFC in 16-bit. Multiplicate with I multiplication, and the result is FC E0. Remember, -800 is FC E0. -800. Actually, the result is FFFFFCE0. Remember, the multiplication done with a word operand will be stored in DX-AX combination. So, this is DX, this is AX. The upper part is keep going FFFF until you fit your memory. So DX should be FFFF, AX should be FCE0. Let's open and look at the DX. DX is FFFF, AX is FCE0. Let's use a bigger number like 40. I want to overflow into DX in order to show you. No, this didn't overflow. Let's put bigger one. Yes, this overflow a little bit. Let's put bigger ones. Yep. $2,000 times minus times 4,000, which is 8 million, but this is minus 8 million. So minus 8 million is actually here. Minus 8 million. This is DX. This is AX. Look at the DX, FF85. Look at the AX, EE00. The result is correct. But if you look at the DX value, it's just something meaningless. You can't separately look for the values. For example, AX is something meaningless. You don't add them. You concatenate them. You combine them. Okay? So this is I multiplication. If you use a word operand, the algorithm will be AX times BX will be stored into DX-AX combination. If you use a byte operand, the result will be, the algorithm will be AL times BL will be stored into AX. In order to store the DX-AX combination, we have to use move operands 2 times, one for DX, one for AX. The lower part will be written into memory first. Oops. For example, I'm going to write this into 1000H, the lower part, and the upper part. I'm going to write the upper part. The upper part is DX, and AX is, remember, a 16-bit word which will be stored in 1000 and 1001. DX is also 16-bit, will be stored into 1002 and 1003. Let's run this code and go over and look at the 1000 address. FF85EE00. FF85EE00. As you can see, 8 million is stored in 1000 hash memory address, which is 32-bit. Any questions so far? No, there is no question. Okay, then I'm going over to next instruction, which is division. Bölme. Divides unsigned value in the AX or DX-AX register by the source operand and stores the result into AX or DX-AX registers. The action of this instruction depends on the operand size. It's actually the same. If the operand size is byte, the algorithm is like this. if the operand size is word, algorithm is like this. Remember, in division, we have remainder. For example, when you divide 17 with 10, the result will be 1, the remainder will be 7. Let me write it in here. 17 divided by 10. The result will be 1. The remainder will be 7. Okay. In here, for example, looking over here, operand is 10. AX is 17. This is AX. This is operand. And the remainder is 7, which is AH. The result is AL. The result is 1 AL. Okay? Now let's go over here and make this division operation in our emulator. Okay, we are going to divide 17 decimal value with 10. I'm going to use BL. BL. This is the program. Emulate 17 is actually 11-hash. As you can see, it's 17. Move 10 in BL and the division operation. Division is done. The result is in here. The result is 1. The remainder is 7. Okay. So, if the operand is word, what is going to happen? It's going to take dx ax combination and divide that combination with bx, and the result will be in ax, remainder will be in dx. Let's emulate this code. Dx is 0, 0, 0, ax is 17, bx is a, and I'm going to make a division. Division is done. Be careful, this time result is in AL, actually in AX, and the remainder is in DX. Okay? According to your operand size, it's going to take DX AX combination. For example, in previous examples, what was the 8 million? FF85. Oh, this is find value minus 8 million. Let's take 8 million. For example, I'm going to divide 8 million by 4. No, it didn't fit. 8 million by divide by 4,000. Okay. Now I need to 8 million. This is 8 million. 7A 1200H. Okay, I'm going to put this 7A part into DX. You can use 007H or 7H, it doesn't matter. The AX part is 1200H, and I'm going to divide this 8 million into 4,000. What was the 4000 value in hexadecimal? It is FA0. I'm going to use 4000. Make the division operation. Let's make again 4000. The result is 7D0. There's no remainder. So dx should be 0th after this operation. Let's go over and look at it. Okay. Dx is 7a, ax is 1200h, bx is 4000, which is fa0, 4000. Now make this division operation. Okay, the result is, as you can see from here, the result is 7d0. Result is in ax, which is 7d0. In dx is 0th. As you can see, there is no remainder. Okay, let's add 1 into or a into our 8 million. Our value is now 8 million. Oh, this is 80 million. Or 8 million and 10. Okay, 8 million and 10 divided by 4000. The result is 7d0, but this calculator is not going to show us the remainder. So let's see what will be the remainder. Okay, 8 million and 10, put it into dx-ax combination. 4000 is put into bx, and division operation is done. The result is 7d0, result is not changed, but the remainder is a. Okay? If you use a word operand in this division, it takes dx-ax combination and divide it with bx. The result will be in ax, the remainder will be in dx. These parts explain this. Okay? Okay, now I division, signed division. It's exactly the same. Nothing is changed, but this time the numbers are going to how can I say, applied as a signed values. Okay, this time I'm going to divide minus 8 million divide by 4000. The result will be F830. The result will be this. Okay, now put minus 8 million into dx-ax combination. Minus 8 million. Okay, this is minus 8 million, which will be FF85H and EE00H. If you use character in here, you have to put 0 beforehand, remember. If you use character at the beginning of this 16-bit value, you have to use a 0 beforehand. Okay, this is minus 8 million divided by 4000. But this time we are going to use I division. Okay, now see the result. Minus 8 million is stored into dx-ax combination. 4000 exactly the same. This is positive. Put it into bx. And the I division operation is calculated. The result is F830. There is no remainder. The result is, where is the result? This is 8 million. 8 million divided by 4000. The result is F830. as you can see, F830. Okay, now if you increase by 1, for example, this is 8,000,001, and I want to see this remainder 1 into dx. Okay. Oops. The result is F831 negative 8,000,001. This is FF85 EDFF. So this is not negative 8,000,001. 8,000,001 is EDFF. So we make it 7,099,9999 like this. So that's why it calculates wrong. Okay. I division is calculated. The result is here, which is F830, and the remainder is here. What is FFFF in remainder? This is actually -1. The remainder is -1. If you open this in 16-bit and look at the signed value, it is -1. FFFF is -1. So the remainder, if we divide 8,000,001 with 4,000, will be -1. We give the example with a word operand. Let's give it byte operand. In the byte operand part, there is no dx. We are going to divide a number, for example, 4,000 into 2 BL, AL. I don't know the hexadecimal version of 4,000. Can I use this? Which is FA0. So it didn't fit into AL. 400. 400 is still did not fit. 255. This should be fit because it is FFFE. FF. Sorry. So this is FF. 255 divided by, let's say, 5. There shouldn't be remainder. I'm going to use BL operand, but sorry, that's my bad. We have to use AX. Because the algorithm is AX should be divided by operand and the result is in AL. Sorry for that. So we put 255 in AX, put 5 in BL, make the division operation. What will be the result? Where is the calculator? The result will be 51. Let's emulate this one. Okay, FF 5. The division, the result will be 51. 32 is hexadecimal, 51 is decimal. There is no remainder. As you can see, remainder is 0. Let's make it different calculation. There should be, the result will be 50, remainder will be 4. Okay, the division is done. Result is 50, remainder is 4. Result is 50, remainder is 4. You don't look AX completely, remainder and result. These are different things. This is result, This is remainder. Okay. If there isn't any question, I'm going over the examples. I think there's no question. Okay. I'm diving into examples. The first example. Write a program that multiply unsigned values of FE and 10 and save the result to this memory location. Okay. Let's write this example. As we can see, these are 16-bit values. I'm going to put one of them is in AL. I have to use 0 beforehand. The other in BL. For example, 10H. After that, I'm going to use multiply BL with AL, and the result will be in AX. And I'm going to store the result into 400H. The result is in AX, remember. Okay, the actual result, what will be the result? 454 times 60. The result will be 4064, FE0. Okay, let's emulate FE. Okay, we put 0 at the end, that's right. FE in AL, 10 in BX, these are hexadecimal. We make the multiplication. The result is FE0. And we are going to put that into 400 memory location FE0. Okay, there's no signed operation. These are unsigned numbers. We multiply 254 with 16. This is the answer. Second question. Second question, numbers are same. This is FE again. This is 10 again. But this time, write a program that multiply signed value. Signed value is FE is -2. And signed value of 10 is 16. This is same. So this number is same. This number is same. I only going to change a single character, add a single character, which is I value. This is the correct version of multiplication. The result will be -32. 32 will be FFE0. Okay, let's emulate this code. Okay, FE10, we are going to I multiplication, and the result is FFE0. As you can see in here, the result is FFE0. FFE0 is -32, which will be stored into 400 memory location FFE0. You can't directly understand what the value of FFE0 by looking at the memory. You know that these are signed values and the result should be signed value. You get the FFE0 from the memory and look for the signed karşılığına, the equal part of this signed value, which is -32. Okay, the second question is this. Third question, this is division question. We make a division. We are going to divide 171 with 10. The result will be 17, remainder will be 10. Okay, the hexadecimal version of this number is AB. Hexadecimal version of 10 is A. We already know that. So AB is 16-bit number. That's why I'm going to use AL again. Sorry, we are making a division. That's why I'm going to use AX or DXAX. This is a small number, that's why I'm going to use AX. I'm putting AB into AX and A into BL. 0A into BL. We are going to make a division operation. Operand is byte, that's why AX divided by BL will be stored in AL. The remainder will be in AH. And the result will be stored in 500. The result is in AL. The remainder, which is should be stored in 502. The question won't show us that. Remainder will be in AH. Let's emulate this code. Okay, AB, which is 171. A, which is 10. Division operation, the result is 17. Remainder is 1. So we put 11H into 500, 1 into 502. Let's go over and look at the 500. Result is 11, remainder is 1. Okay. Same numbers, but this time we are going to get them as a signed value. Numbers are same. Okay. In order to calculate AB as a minus 85, we have to put this value into AL, or we have to put this into AX as a FFAB. Let's not change anything. The previous example. This was the previous example. I'm going to just change IDIV again and see if it is calculating correctly or not. We put AB into AX, and I'm going to look at the signed value of AX. Yes, this is wrong, because it should be minus 85, but it is 171. We have to look for the AX value. AL is correct, but AX is not. In division, we divide AX, that's why this is wrong. I'm going to put FF beforehand and look for the AX value. Now it's correct, minus 85. This will be the correct version. Or can I only use this way? When I put AB in AL and look for the AX value, no, I can't. So the correct usage is this. Minus 85 in AX should be FFAB, not just AB. If you open the calculator and write minus 85, you get the F's beforehand. Our AX size is 16-bit, so 16-bit AX should store FFAB. Okay. Okay, now divided by 10. 10 is also 10. There's no change in 10. So result will be 8. Remainder will be minus 5. I division is done. The result is -8. That's right. The result is -8. Remainder is -5. That's right. Okay, that's my bad. The result shouldn't be 8. It should be -8. Okay, these values should be stored into 500 and 502. Let's go over and look at the values. This is F8, the result. F8 is -8. FB is -5. But look at here. I want you to be careful. F8. This is hexadecimal version. This is decimal version. Decimal version is 248. It didn't give us the -8 because this memory part, this part, only show the unsigned version of this hexadecimal part. But we know that these numbers are signed values. That's right. That's why these are wrong values. So this should be -8. This should be -5. Okay, be careful. This is important. By the way, you can directly use -85 as a decimal. He's going to put FFAB into AX. Okay, this was the last example. Any question about the lesson, example, emulator, minus things, anything? We give a bigger examples in beforehand. Remember, -8 million divided by 4,000. We look at the division parts, remainder parts. These examples are only work with bytes. So there isn't any question. I'm stopping this record.